Another feature of language that's super interesting is that language itself evolves. It clearly evolves faster than biological creatures evolve.
By
Language,
orders of magnitude, yes.
yeah, much faster. And you've written that there are basically that language is subject to selective influences that are probably quite alien from those that affect our brains and bodies. So, what exactly do you mean by a statement like that?
Well, so number one, language learnability is going to be an issue. Languages that are learned at a young age and learned well are going to be passed on more effectively. They're going to be more stable over time. So there's particular aspects of language, particular phonetic structures that are difficult for young children to acquire. They're probably not going to be passed on well. Certain combinatorial effects, syntactic effects that are quite complex, that are not, you might say, intuitive, will not be picked up early on. We'll have to wait until sort of later childhood to get these complexities. But as a result, they will also not be passed on as well, in part because early on the brain is very plastic. And what we acquire early on tends to be more easily automated and harder to get rid of. So in terms of, if we think about language evolving, it has to have a reproductive component. And then it's got selection on it. Those things which are reproduced more stably and with more fidelity over time, that means they're going to be more learnable. So I think one of the things that's happened is that languages have evolved and have to evolve to be more learnable at an earlier age. So one of the things that we find is that children can learn multiple languages easily if they're exposed to multiple languages at a young age, before they're age 3 and 4. But only a few of us do pretty good at learning multiple languages well after that period of time. This is telling us that languages, to some extent, language evolution and language change, and therefore language acquisition, is going to select for languages that are easily learnable and learnable at an early age. So the structure of language evolution has got selection features. We're selecting our nervous systems, our development, our ways of communicating are all part of the, you might say, the environment to which languages have to adapt. One of the things they have to do is they have to adapt to brains and how primate brains and how human biased brains still acquire this. But in particular, if they can do it to younger brains that don't learn quite the same way that older brains do, that have certain disadvantages and certain advantages, those languages are going to be passed on better. And those features of those languages are going to be the languages the features that most languages inherit. So I think language evolution has to be thought of in terms of it's evolving to us, to be adapted to us. It's not evolving because it's an organism, but it has many of the same characteristics.
Yeah, in many ways, it behaves sort of like an organism, even though it's not.
Clearly not an organism. And of course, the interesting thing is it's distributed. It's not just in me. It can't be just in a single individual. It has to be distributed. So it has a lot of interesting statistical features that will have to do with social groups and how groups form and break up. That's going to affect it. So languages have to have this capacity for conversation, for asking, for telling, for explaining, all of the features that languages have to do also with the fact that they're a social phenomenon. That's part of the selection, the environment in which languages evolve.
Given that, given what we were talking about in terms of how language evolved, the types of things people are most concerned with that they use language for, around mate selection, around trusting the individuals you have to interact with to stabilize the social structure. We all the things that we were discussing. What do you think the consequences of the global our sort of globalized population structure is today. Like we no longer live in bands of dozens or just a couple hundred people where everyone you know and interact with is literally at your wedding. How do you think that and the technologies we use to communicate today, our smartphones and all of this stuff, can you anticipate any ways that might cause our language to evolve in a different kind of way than it has historically?
I'm not sure it will cause our language to evolve in different ways, because we're mostly using it in person-to-person interactions, even like we are today across long distances and so on. But I think one of the things that will happen is that we're going to be shifting more and more onto social phenomena. So, in the past, when you wanted to make an agreement, I couldn't trust you just to say, your words, just I promise to do this. Now let's shake hands. Let's touch. And that means, so we've got an index here of agreement. We're not fighting, we're agreeing. When you can't do that, maybe what you can do is have a different kind of index. I give you a piece of paper that has some things that you read, and they say this is what you can do and you can't do. You have to indicate that you agree by writing your signature on it. Your signature says that I was physically there. I was physically there, exposed to this. This is an index. It's a much more powerful link than just the okey doke of language. Language is disconnected in a way that a signature is more connected. We're now developing ways of doing that at a greater distance. One of the features is that as we begin to offload those direct interactions, issues of trust, issues of cooperation are much more difficult to maintain. And we have to develop extra tools to do this. One of the challenges is that also, I think the internet has done something else, that we've constructed these systems based upon, you might say, a logic that's irrelevant to the communication. So, for example, in order to keep people looking at a particular website, I've got to make them like it. I've got to make them, find, oh, this next piece of information is more interesting. I'll follow that. So just for the financial structure of creating these systems, we've created certain biases in transmission. We've now noticed the consequence of these biases, that negative information, that surprising information, that threatening information, explicit sexual information. This stuff tends to be reproduced much more rapidly. So there's a different selection pressures have come into play, and they come into play very rapidly of what gets communicated. And that's going to structure things very, very differently. I think one of the things that I'm looking forward to, but not quite clear how it's going to affect us, is the way that artificial intelligence is going to allow us to communicate across languages effortlessly. That is, simultaneous communication is going to be what everybody has available to them, as we have knowledge available to us by looking at our smartphones these days. All of that's there. But notice that this is going to get us back to where we started in our conversation about redundancy. I start one of the chapters in my book by talking about smartphones and how we've become addicted to our smartphones. I no longer know the numbers, the phone numbers of people I used to know. I no longer know addresses, but I now have access to hundreds of more addresses and phone numbers than I ever had before. But if the power goes out, if the grid goes down, I'm really disadvantaged. I've become addicted at the same time. But this leads me back to a story that's as ancient as philosophy itself. In Plato's Phaedrus, Socrates says that if men learn writing, they learn writing and reading, it's going to degrade their memories. They're going to be stupider. Maybe this is not a good idea. And yet, obviously, we've learned reading and writing. We now have offloaded a lot of memory onto this stuff. I don't necessarily know all the things that I've actually learned in classes, but I can go back to the books and find it. But because of this, of course, I also know what Socrates thought or what Plato thought.
Right.
Yeah, of course, it degraded some capacities, but it gave us other capacities. This is that relaxation effect. There's been a relaxation of selection on memory, but it allowed other things to develop. That's happening socially. I think it's going to radically, in the next generation, over the next couple of generations, radically change the structures of societies. I'm not sure it's going to do it in all useful directions, but it will radically change it.
A lot of people are now using and talking about and speculating about things like generative AI. So when you look at technologies like ChatGPT and these large language models, we call them large language models because we're feeding in human text made out of human language into them.
Text. Yeah.
In what sense are these systems using or not using language and symbolic cognition?
Well, one of the things that I think is most interesting that's come out of this work is that we can also use large language models sticking in these letters. We have 20 letters for all the amino acids in a protein. We know the structure of some proteins. One of the problems is that we have not known for years and years how the sequence of amino acids cause proteins to fold.
Mm-hmm.
It turns out now, beginning first of all with a group called out of OpenAI AlphaFold, they fed in what we know about which amino acids follow which amino acids and how that causes a protein to fold. We know the folds of those proteins, some that we know. Can we now just sort of train it on all those that we know and now feed in a random sequence of amino acid letters? And will it tell us how something folds? Well, it turns out that AlphaFold and now 3 or 4 different versions of this have used a large language model structure to predict how proteins fold. Now, here's the important thing. Proteins fold because of their chemical environment. They fold because of hydrophobic and hydrophilic effects, because of stiffness effects, and so on, because of the sequence of which they come out. Some are exposed to an environment before others are. It's a complicated physical chemical process. The large language models that predict protein folding don't know anything about the chemistry or the physics. And yet they're able, using this huge statistical capacity, to make good predictions about how proteins will fold. We can now use this statistical prediction to go back and figure out. In other words, we've got, it's like, I want to learn the math by going to the back of the book and looking up the answer before I can figure out how to use the equation. Mm-hmm. That's what we've got. We've got the back of the book. There is no knowledge in the system. But the skeleton of the process, you might say the syntax, or you might even say the fossil of that information is there. It's structured. Those physical processes produced structure. And now we can use statistics to look at the correlational structure and then use that correlational information, once we've got the structure, to go back and try to analyze, to learn it. So this is helping the science. But now let's think about this, the same analogy for language. We have terabytes of conversations on the web that were scoured to build into these systems, and then testing them on predicting how well it produced. Auto-correction kind of thing. The structure of that communication that was on the web was structured by people's interests, by meanings, by references, by things in the world, by science, by literature. The structure was produced there. That's the analogy to the chemistry and the physics of protein folding. But notice that the large language model doesn't have any of that. It's not related to the world in any way. It's completely isolated, but it's got the structure that was there. I like to think about it as the fossil of the living speech, the living communication. But if we've got enough fossil evidence, we can reconstruct this, and now using our knowledge of language and meaning and reference, we can now do what the biologists could do, looking at protein folding, and say, I can use that information and I can reconstruct its meaning. It's, in the case of the molecular biologist, I can learn something about the chemistry of it in terms of you or I using this generative AI. I can learn something about the meaning of something that I might not have known. I can use it to create a Shakespeare sonnet about planets and solar systems. Why? Because it's got that structure. But that structure, since it carried with it all the biases, all the structured biases of communication, when I pump new stuff into it and have it come out, it'll come out in a way that's interpretable. It gives me information. So I think it's going to be incredibly useful. But of course, as we know, it can be incredibly troublesome as well for all the same reasons. But this is why these new technologies are going to be very useful in the sciences, because they're giving us the answer before we know the details of the question yet. But we can use it, we can retrodict. We can use it to go back and figure out, okay, that gives me a clue as to how it was formed. Maybe I can use that. The problem is that we tend to fail the Turing test here. We're so gullible. It produces something that looks like it understands something, and we think, oh, it's got understanding, it's got a mind, it's got sentience, it's got thoughts. None of that stuff. Any more than simulating the movements of planets on a computer is gravity. There's no gravity, there's no mass. It's just the formal structure, but it's enough to do incredible things. We can use that formal simulation to guess at new laws. We can use the simulation of protein folding in these systems to get at the chemistry and physics.